So today we're going to take a quick snippet from what would have been Unit 5. Because of time, we do cut out the rest. Like I said, this is going to carry over to Algebra 2 quite a bit. And it's on a topic that we've kind of seen a little bit before, but we hadn't gone into a whole lot of detail on, and that is radicals. So for our purposes, we've referred to radicals as square roots. That was the particular type of radical that we used, particularly in the quadratic formula, where we grabbed our calculator, took the square root, approximated, and went along our way. But there's actually several more radicals out there. Square root is just the most common one. So it says here that a square root is the inverse operation of something that's being squared, that is raised to a power of 2. Square roots are one of the many different types of radicals that exist, and I'll show you a couple other ones here. And we're going to use this diagram here to identify them by name, the parts by name. Now, we've kind of already talked about the fact that they are inverse operations. Every operation has an inverse, just like addition has subtraction, multiplication has division, squaring something, and square rooting something are considered opposites as well. So in this little diagram here, we have some pieces. Most of it looks pretty standard. There is a little value here we'll pick out in just a moment, but we're going to start with probably the most iconic piece. That is this weird check mark with a bar looking thing. This is the radical sign. That is the radical sign. Now, like I said, for our purposes, we've been calling it a square root. And that is because that is one of the radicals, well, the only radical we've considered, but the very broad term is a radical sign. Now, the radical sign is an operation, and what it performs its operation on is everything inside, which is referred to as the radicand, which every time I say that, for some reason, I think of a Pokemon. Kind of sounds like a Pokemon name, but it's referring to everything contained within the radical sign. Now, in this case, it's just an X, but later on, there's no limit to what you can actually contain within a radical sign. You can have an X, you can have an X plus 3, you can have a big trinomial or polynomial, or a whole large expression inside the radical sign, and that would still be considered your radicand. The whole thing is conditional to the radical sign. Now, the piece that is new, the piece that we haven't specifically addressed, is this little value here, which is being denoted by n. This is what's known as the index. Now, the square roots we've been dealing with so far have had an index, but it is the one index that is hidden a majority of the time. So off to the side here, I'm going to make a little note. The square roots, so let's say the square root of 4, for example, which hopefully we all know is 2. Actually, let's not do 4, because sometimes people think radicals are the same as division because of 4. Let's do the square root of 9. The square root of 9, we know, hopefully, is 3, because 3 squared is what makes 9. Now, for our purposes, this is how we've seen it so far, and it's usually the way it's expressed on our calculator, but this is the same as saying it is a radical with an index of 2 of 9. The only difference is, for the most part, our index we've been using has always been 2 for the square root. But because it's the most basic, or it's the first square root that we have, its index is typically hidden from us. But these are referring to the same thing. The square root of 9 is the same as saying the second root of 9. Therefore, an index of 2. So a little note here. A square root specifically always has an index of 2 but it is most often hidden. So, quick technical error. But yeah, so a square root specifically always has an index of 2, but is most often hidden. So we don't typically see it when we're dealing with square roots. Now, if you wrote it there, it's not going to be wrong, just for the same reason that anytime you have a hidden coefficient, if you wrote a 1 there, it still represents the same thing, but it's there. This is the one time that it's a 2 that's hiding instead of a 1. So there's the diagram again. So again, the terms that we throw around a little bit, we have the radical sign, which is kind of the main focus today. Everything inside of it is considered the radicand, and the index, which is the little value outside of the radical sign, that tells us which root we're looking for. Now, today specifically, we're going to focus on square roots, but the trick I show you works on all roots. So our main focus today are going to be square roots, but it is worth mentioning that there are other roots out there other than just the square roots that we look at today. In fact, there is a corresponding root or radical and index for every power that you can think of. So, we didn't just square things. Sometimes we can raise them to the 3rd power, the 4th power, the 5th power, and so on and so forth. And for every power that you can think of, there is an inverse root and index to offset it. So for example, if you have something raised to the power of 5, the inverse operation of doing that would be taking the 5th root of it. Now, if it's anything other than a 2, you have to see that index there because that's signifying the difference between one radical and the next. But what this is saying, for example, let me use off to the side here, 2 to the power of 3. If you think about it, 2 times 2 is 4, times 2 is 8. 2 to the power of 3 is 8. If you took the 3rd root of 8, you would get 2 again. So when we take the square root of something, we're asking what times itself twice gives us that value. If you take the 3rd root of something, you're asking what times itself 3 times gives you that value. And so there are not only perfect squares, there's what are called perfect cubes. So numbers that are created from multiplying the same number 3 times. There's perfect fourths and fifths and sixths and so on and so forth. Now, don't fret too much. You will spend more time on this as well in Algebra 2. This is just a quick preview. There are more indices out there because there are more powers than just powers of 2. But like I said, today our main focus, we're not looking at all those other powers. We're only worried about perfect squares, and therefore its inverse, the square root. And what's going to help us today is to have at least a decent list of perfect squares that we can consider. Now remember, perfect squares do go on forever because any number you can think of, if you multiply it by itself, it creates yet another perfect square. But what I've got here for us in our notes is a split table here. We're going to list the first 20. So far, I've only given you the first 10, but we're going to list the first 20 perfect squares because knowing these values will help us with what we're about to do in just a moment. So we've listed the first 10 before, but let's do it once more so we have it all in one spot. So 1 squared gives us the perfect square of 1. 2 squared gives us 4. 3 squared gives us 9. And then so on and so forth. We get 16, 25, 36, 49, 64, 81, and 100. So those are the ones I've given you a variety of times. Like I said, that list can go on forever. 11 squared gives us 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. Hopefully someone's fact checking me here. 15 squared, I believe, is 225. And that's usually as far as I can remember with confidence. What's 16 squared?
256.
256. 17 squared?
289.
289. 18 squared?
324.
324. 19 squared?
361.
361. And I know the last one is 400. Now, like I said, this list goes on forever. We could do 21 squared, 22 squared, 23 squared, forever and ever and ever, and continue to get a never-ending list of perfect squares. Now notice they're getting further apart, and that's just because we're multiplying a larger number each time. But this list could go on and on and on. The numbers that we're going to be looking for today should not go beyond this list of values, however. So anything that you'll need, possibly, we're going to refer back to this table. Or perhaps our factor pairs if we want to as well, if it helps. What's that? Yes, but that's not on the list. We'll talk about that here in just a moment. So this table, kind of along with your factor pairs, this is going to be a valuable list of information. And this is a list that anyone could make with even just a basic calculator. If you just sit there and multiply two numbers, the same number together twice over and over and over again. But what it's all leading up to is giving us the ability to simplify square roots first with constants, so no variables, and then we're going to add variables just to spice things up a little bit. Yes, I got it.
24, square root of 7 and 10.
The square root of 24 is 7 and 10?
Yeah.
Not quite.
Oh, come on.
So we'll talk about that here in just a moment. So in the past, not too distant past, in the quadratic formula, we would run into situations where we had to take the square root of values that were not perfect squares. Taking the square root of a perfect square is all fine and dandy because you get a nice clean number, but any other numbers, you get a decimal that goes on forever and ever and ever, and we had to round. Now, depending on the work that you're doing, approximations may not be good enough. You may want to deal in exacts. So what you have to do is instead of getting rid of the square root altogether and rounding, you have to simplify that square root the best you can so you can perform additional functions with it. So in order for square roots to remain exact with non-perfect squares as the radicand, they must be simplified by pulling out all factors of the radicand that are perfect squares. I'm going to highlight that. Simplified by pulling out all factors of the radicand that are perfect squares. Now, we've looked for factors in the past. we needed to know factors for our asterisk method. Today, we're still looking for factors, but we're looking for special factors. In particular, factors that are also themselves perfect squares. So the best way to see this in action is by doing. We're going to start with the square root of 24. And just for the sake to test a theory, in a calculator, if you don't mind, Leanna, what is the approximate value of the square root of 24?
4.898.
898. So that would be, I'm gonna round that up to 4.90. Great. If we're dealing with approximations and this was close enough, awesome. This would work perfectly. But let's say that we're an astronaut and we're recalculating re-entry to the Earth's atmosphere. We have a very, very narrow margin where we either bounce off, go out into space, die from lack of oxygen, or we burn up on re-entry and then therefore also die. So close is not close enough. So I need to simplify this down so it's got smaller pieces, but still retains the same value. So I look at the number inside the radicand here, 24. What are some factors of 24? 2, 4. Well, let's list them in pairs. We've got that on our factor pair list. 1 and 24, we'll start there. Okay. 1 and 24.
2 and 12.
2 and 12.
3 and 8.
3 and 8.
And 4 and 6.
4 and 6. Awesome. A lengthy list. But do any of those factors stand out in any particular way? You've got the list in front of you, hopefully. Any of those factors?
4 and 6.
4 and 6. Why is 4 and 6 standing out to you?
Because the 4 is a perfect square.
I couldn't have said it better myself. 4 and 6. 4 is unique because it is a perfect square. And in the world of square roots, perfect squares work nicely. So let's say, for an instance, instead of leaving the 24 inside, let's rewrite it into smaller parts. We know that 24 is the same as saying 4 times 6. This is still the same expression. I'm not trying to solve anything because there's no equal signs to solve with. All I did was say that 24 is the same as 4 times 6. Now, Leanna already said that 4 is special because it is a perfect square. In fact, I could take the square root of it quite nicely. Now, here's the neat trick. Square rooting and squaring things really is just a really fancy form of multiplication being manipulated in a variety of ways. And as a result, when you have 2 or more numbers multiplied in the radicand, instead of taking the square root of all of them all at once, you can actually take the square root of them individually. So this is the same as saying that this is the square root of 4 times the square root of 6. It's the same thing. The square root of 4 times 6 is the same as the square root of 4 times the square root of 6. It's just an equivalent statement. But which of those two do I like? That square root of 4. What is the square root of 4? 2. So I get 2 times the square root of 6. Now 6 is not a prime number. So I'm a little worried. Maybe we missed another perfect square somewhere. What are our factors of 6? 2 and 3? 1 and 6. Now technically 1 is a perfect square, but if it's paired with what number?
6.
So taking 1 or 6 and breaking it into 1 and 6, are we breaking the 6 down at all?
No.
We're still going to have a 6. So 1 is the only perfect square that's not useful today. It's often left out. So what I'm left with is 6. It's not prime, but it can't break down into any more perfect squares other than 1. We were able to set that 4 aside. That allowed us to square root it and get the 2. We're now left with this interesting expression, 2 times the square root of 6. If you don't mind for me, Leanna, real quick, what is the square root of 6?
2.45.
2.45, so on, so forth. Without clearing off your calculator, multiply that by 2.
4.8989.
4.8989, which if we were to round it, is still that approximate value of 4.90. And it should be, because 2 times the square root of 6 is the exact same as the square root of 24. It's the exact same value. All we did was simplify it. Now, because it's square roots and it's a little bit different, students kind of freeze up a little bit, think, this is strange. But go back to math A and math B. If I said, hey, I've got a fraction, 4/6, what is that equivalent to?
Lee taught us this in her class, so.
She taught you this in her class as well, so you got a head start. But if I said 4/6 is the same as, what's that? Not quite. You can take a 2 out of both 4 and 6.
0.6.
As a fraction is 2/3, but they're still the same value. 4/6 of something is the same as 2/3 of something. All you've done is change the pieces that describe it. You haven't changed the value. You haven't changed the amount. Simplifying the square root is similar in that sense as simplifying a fraction. You're not changing the value, you're changing how it's expressed. Now, it's going to get really boring because we're going to just do a lot of practice of these today, but it's going to be something that will hopefully help you when Andrea then in Algebra 2 says, all right, guys, let's use the quadratic formula, but when we get to the square root, instead of putting it into our calculator, let's just simplify it. So I'm going to drive it home today with you guys. That way, when you get to Algebra 2, you're like, I've done so many of these, I could do them in my sleep. So let's move on to square root of 18. I'm going to show you a little shorthand method that I like to use just to save myself some steps. You're welcome to use it, or if you want to break it down like we did on this last one, you can. But 18, is 18 a perfect square?
No.
No. Does it have any factors that are perfect squares? Well, one, I have a problem with that statement for 2 reasons. 8, first off, is not a factor of 18.
You could break it down, sorry.
You're fine. I won't pick on you for just a moment. 8 is not a factor of 18. It's also not a perfect square. So it won't quite help me here. But you do have the factor pair list. 2 times
9.
9. Which of those 2 values do I like the most? 9. Why the 9? What's special about 9?
9 is a perfect square.
9 is a perfect square. It's on that table from the front side of our notes, which means if I were to break this apart, can I take the square root of 9?
Yeah, 3 times 3.
3 times 3. So the square root of 9 is going to be removed as a 3. So it would no longer be inside the radical. Can I take the square root of 2 nicely?
No.
No. In fact, it's a prime number, which means I can't even break it down any further. So because of that, it's going to be trapped inside. So I leave it be. So the square root of 9 comes out as a 3, slides out in front. The 2 stays inside the square root. What's our final simplified form?
3 to the square root.
3 square roots of 2, or 3 times the square root of 2.
That seems easier than the other one.
Well, all I did was, this was the mathematical reasoning as to why I can do this little shorthand method. So it's the same math. I just have to validate and say, well, this is why we're allowed to do it. Now we're just going to do it. 96, was that on our list of perfect squares?
No.
No. So this should also be on our factor pair list. Does it have any factors that are perfect squares?
6 and 16.
6 and 16. Okay. Which of those is special?
16.
16. Can I break 6 down any further?
Yeah, no.
Well, I could,
Yeah.
but we've done this before. 6 isn't going to break down to any more perfect squares other than 1. So I know that 6 from past experiences will stay trapped inside. When you take the square root of 16, what do you get?
4.
That's going to come out as a 4. So we're left with what?
4 times the square root of 6.
4 times the square root of 6. Now, before you jump the gun on the next one, 180 very clearly is not on our factor pair list. Now, in the past, especially with the asterisk method, I said, that's okay, go ahead and make your own list. Divided by 1, and then by 2, and then by 3, and then by 4, and so on and so forth until you started to cycle back around, and then you could say, yep, I've got the factor pair list for that value. Here's the good news though. We don't need to waste time with just any factors. What factors are we most interested in?
Perfect squares.
Perfect squares. So instead of dividing it by 1 or 2 or 3, which don't help us, let's first divide it by 4. Yes, it got.
I do 2 times 90 is 180.
2 times 90 is 180. Unfortunately, though, neither of those are perfect squares. That's why we skip over 2. Did 4 work?
4 times 45.
4 times 45?
Yeah,
Another one that's both a perfect square.
it's 4 times 45.
Well, let's talk about it real quick. So hold on. So we don't forget. So I'm hearing 4 times 45,
I have 20 times 9.
20 times 9.
They're both perfect square.
Well, they're not, 20 is not a perfect square.
No, but 9 is.
9 is, and that one's certainly larger, but well, if there's more than one perfect square here, it probably would save us some work if we made sure we found the largest. What's the next perfect square we could check? After 9.
10.
10 is not a perfect square.
$12.
12 is not a perfect square. If you're confused, go back to the list from the first side. We know 4 is a factor. We know 9 is a factor. Is 16 a factor?
But 16 can't be divided by it.
16 does not divide nicely. Okay, well, that's all right.
You get 11.25.
So 16 is out of our list. What about 25?
No.
No. 36?
Yeah,
5 times 36.
5.
5 times 26.
So let me add that to my list. I know it's going to seem a little backwards here, but if you notice, I've got all my perfect squares here on the left-hand side. Now I could keep going, but take a look at this last one we just identified. If I stopped here, can that 5 break down any further?
No.
No. So if we took the 36 out by square rooting it, we'd be left with a 5, which is prime, which tells me that's the largest one that must be there. So I could rewrite 180 as 36 times 5. The square root of 36, hopefully we know, is 6. And 5 can't break down any further, certainly not with any perfect squares. So what are we left with?
6 times the square root of 5.
6 times the square root of 5. Now, because I hope that there are some inquisitive minds out there, I usually get a question, not always, but usually, as to what happens if I accidentally used one of the smaller perfect squares. Well, let me show you. So let's see what happens hypothetically if instead of looking for the largest perfect square, we took the first one we found, which was 4. So off to the side here, square root of 180. Let's say instead of breaking it down into 36 times 5, we broke it down into 4 times 45. Well, so far we'd be content. We'd say the square root of 4 would come out as a 2. And we would say, well, 45 is left inside. So we'd have 2 times the square root of 45. But for me, my gut instinct is telling me 45 is still a relatively large number. And I have the sense that there's probably another factor hiding in 45 that may also be a perfect square. Can you think of any? This one is on our factor pair list. Look at the factor pairs of 45. Any of those numbers jump out at you?
5 times 9?
9 times, you said 5? 9 times 5. So I could technically break down the 45 into a 9 times 5. Well, I know that the square root of 9 is a 3. And that leaves me with a 5 left inside. Well, this is a little uncomfortable because now I'm trying to bring a 3 out and there was a 2 already there. Guess what they're going to do with each other?
Multiply.
They're going to multiply. 3 and 2 will make 6. And what we're left with inside is the 5. Does that look familiar? And it should be. It should be, because what we did here is we took the fastest route first by looking for the largest perfect square. Over here, we kind of had to do double the work because, yes, we took out a perfect square, but then we had to take out another one. Now, aside from the fact that it took longer, could we say that one of these methods is better than the other? Time aside? Or did they result in the same thing? Put everyone to sleep at this point. I would say that they both work equally well, but me being mildly lazy, I'd rather just do that process once by looking for the largest perfect square possible instead of taking the first one I find and then realizing, oh, I have to do it again. What I'm saying though is I don't care which of these paths you take because they both take you to the same result. It's just how much work are you comfortable with doing? So that's a little side note there for us.
So always go for like the largest square root.
Yeah, so what I usually suggest when I'm making my list, kind of like we did earlier on, and I find my first perfect square, but I look at what its counterpart is, I ask myself, does 45, could it possibly be hiding any more perfect squares? And if I suspect that it is, I keep going. I try the next perfect square, and then the next, and then the next, and then the next, until eventually either I've exhausted all my options that even seem reasonable, or if I just decide, okay, let me go back to the beginning, let me try the two-step approach. I'm okay, you know, whatever you feel most comfortable with. Let's try another one. Not too surprising here because we've already now dealt with what happens if there's a number already out in front, but let's see it again in action. First off, that 32 as our radicand, is it a perfect square?
No.
It is not. But if I look at my factor pair list, does 32 have a factor that is a perfect square?
2 and 16?
2 and 16. We could do 4 and 8, but then again, if I think 8, I know also has a factor of 4, so that would lead me to suspect that maybe it's not the largest. So you always want to look for the largest perfect square just to save yourself some extra work. So in this case, I can't take the square root of 2 or break it down any further, so it's going to stay trapped inside. But the square root of 16 is going to give me a 4. And similar to the earlier example that we did, when it comes out and mixes with the number that's already there, all we have to do is multiply them. And in this case, 4 times 8 gives me a 32 now on the outside, but inside the radical, we still have a 2 left over. Let's keep going. 150 is the radicand for our next one. Is 150 a perfect square?
No.
No, it's not on the list that we made earlier. 150 does run off the factor pair list that I gave you. So instead of just dividing 150 by any old numbers, looking for your own factor pairs, why don't you divide them by the perfect squares, starting with 4 maybe? 25 times 6. Sounds like we found one already. Now let me ask you real quick, thinking ahead, can that 6 break down any further to my advantage?
No.
No, in fact, that's the 3rd time now we've seen a 6. Hopefully we're starting to realize that once we get a 6, we know that one's done. The 25, however, when you take the square root of 25, you get 5, which removes the 25. What's it going to do with the number out in front? Mix with it through multiplication. So 5 times -5 is going to give me a -25. And what is my radicand that's left over? 6. Let's keep the ball rolling. Is 72 a perfect square? Don't believe so.
No.
But it does fall on our factor pair list, so a little bit easier. Do you spot any factors of 72 that are also perfect squares? Remembering that we ideally would like the largest we can find.
2 and 36?
2 and 36. Good, you overcame, what is it, 9 and 8?
But if you, yeah, but that goes perfect square.
8 is not a perfect square. 9 is.
9 and
8 is hiding a perfect square of 4. So if I did the 9 and 8, I'd have to do it again to break the 8 down further. But the 2 and 36, well, that gets me right to where I want to go, because I know 2 is not going to break down any further. It is the smallest prime number we can have. And the square root of 36 is going to give me a 6, which will then multiply with that -2 that's already waiting for it outside. So I get a -12 times the square root of 2. Okay. On to the next one. 196, is that a perfect square?
yes.
It is. And I was watching you, Tierra, to see if I caught you. You first shook your head no until you looked at your list. I fooled you a little bit. 196 actually is a perfect square. Is there any reason to break it down then?
No.
No, because what is the square root of 196?
14.
14.
I knew it was coming. I just didn't know when. That's why I checked myself.
And then 8 times 14 would give me
112.
112. So the reason why I threw that one in there at the end is because what I don't want to happen is for you to get tunnel vision and assume that everything inside a square root now has to be broken down. Sometimes we get lucky and land a perfect square in there already. And if that's the case, it'll save you a little bit of work. So don't get tunnel vision and think that you always have to break it down. Now, if you had broken that one down and went through the process, eventually, hopefully, if you stuck with it long enough, you would have still come to the same conclusion, but then you would have done twice or three times the work necessary. How do you feel about those? You feel comfortable breaking down larger numbers into
Good.
factors?
Yeah.
Good. Leanna, you said you already did this with Leah, so that's perfect. So that's awesome. This is the second time you'll hear it. So third time you'll hear it again is in Algebra 2. And at that point, then I think she throws in third roots as well, which works the same way. Instead of looking for perfect squares, you look for perfect cubes. Don't panic. Remember, you learn new things every day.
My anxiety was rising, and then you said don't panic.
Someone else agrees.
Yeah, so again, you'll get to that point, and when you get there, she's going to show you similar methods, and you're going to be like, I remember doing something like this with Josh in Algebra 1. And what you'll do is you'll reapply the same skills that you have. So again, I don't think I've ever specifically said it, but it may be a good idea to hold on to these notes, because sometimes she's going to refer back to previous skills. And if you're like, oh, I kind of remember it, but I kind of need a refresher, you can go back to those materials and look over them. Google Classroom as well, will still be available to you, I believe. It will be in your archived classes though, because at the end of each term, I archive the class. But you'll have access to those resources as well. And I'm going to be a YouTuber here for a moment. If you subscribe to my channel, you'll still have access to all those videos for the notes that I've done so far as well. So those resources don't go away. They're there if you look for them and if you need them.
I think I'm going to need a bigger notebook.
Yeah, and if you think about it though, I've come a long ways. I used to do 3-4 pages of notes per lesson. I've got it down to 1 sheet of paper, which is, I never thought I'd reach that moment. All right, well, it wouldn't be algebra if we didn't throw in some variables. So how does this process look if there are variables in the mix? So here's a clue. Simplifying a square root that contains a monomial instead of just a constant uses the same idea for hidden perfect squares within the monomial itself. But there's a very, very important hint that's going to help us out here. When a variable is raised to a power of 2, it is considered a perfect square. Well, duh, something squared is a perfect square. So we've kind of got an unspoken goal here. We know how to break down the values. The variables, I know that I'm happy if I can get it as something squared. So again, the best way to just see it is by doing it. And what I'm going to suggest is let's start where we're comfortable. Let's start, with the piece that we've been working with so far, and that's going to be that 48 here. Is 48 a perfect square?
No.
It is not. But if you look at your factor pair list, does 48 have any factors that are perfect squares? 3 and 16. 16 sounds awfully large. 3, I can't break down any further. I would say 3 and 16 sound like some likely candidates. So far, same as above. Then we get to the variable. We have a to the power of 3. Now my hint said that I really like variables to the power of 2 because I can treat those as perfect squares. Clearly that is not the case here. But let me ask you, is there a way you could change a to the power of 3 to show a hidden a to the power of 2? It's kind of a deep thought exercise. Give you a clue. The trick is all in how you group the variables together. Right now, they're just grouped into
Can you
one
separate
big.
them?
Separate them how? How would you separate them? Go with that.
On minus an A.
You take an A and set it aside?
Yeah.
Okay, so if I were to do that, if I'm hearing you correctly, that would look like a to the power of 2 times a. Now, correct me if I'm wrong, if I were to multiply a to the power of 2 times a, that is still a to the power of 3, because there are still 3 there. Go all the way back to our exponent properties, multiplying the same base. You add the exponents. That is still the equivalence of what's above. But why do I like it written this way better?
Because you got the A squared.
I've got the a squared, and technically that's a perfect square, right? Well, let's see where this takes us. Starting with the 3. Is 3 a perfect square?
No,
Can I break it down any further?
no,
Is it trapped?
yes.
It's trapped inside, so I'll circle it. Can I take the square root of 16?
4.
Square root of 16 gives me a 4, which means the 16 is no longer inside. Now we get to this a squared, which kind of piqued our interest. What do you think you get when you take the square root of a squared?
Perfect square should be A squared.
You wouldn't get the same thing.
You just get A.
You would get what's being squared, which is this case, the a. Can I take the square root of a?
No,
No, it's not a perfect square because it has to have an exponent of 2. And can I break a single a down any further?
no,
No. So is it trapped?
yes.
Okay. So guess what the 4 and the a that we pulled out are going to do?
Go beside each other.
They're going to go beside each other. They're going to slide out to the front. They're going to be multiplied together, if you wanted to technically specify. So we're going to have a 4a outside our radical, but what's still trapped inside our radical?
3A.
A 3a. That's it.
So I got it right.
You got it right. So good. I've got one surprise still up my sleeve then. I still had something I could teach you. So the goal is still the same. We're still going to break things down to find perfect squares. Variables are just a little bit different because we want to group them into groups of 2. Let's move on to the next one. 128, is that a perfect square?
No.
Nope. And it's not on our list from 1 to 100. So 128, start dividing it by perfect squares. Does it divide by 4?
Yes, 32.
4 and 32. 32 seems awfully high. That makes me suspect that there's a larger perfect square we could find. So try dividing it by 9 and 25 and 16 and so on.
You can get 8 times 16.
8 times 16. So that sounds better, but I do know for a fact that 18 is also hiding a 4 in it. So I'm thinking, let's go even larger. And this one might take you a minute because you're going to get a little tired looking until you finally find it. I promise.
64 times 2.
64 times 2. I know that 2 can't break down any smaller, but 64 is a perfect square. What about that x? Can I break it down? Because right now it's not to the power of 2. Can I do that little trick I did earlier?
No.
Why not?
Single X.
There's only a single x. You can't make more appear if there was never any more there to begin with. So that x is just still sitting there. But now that we've broken things down the best we can I take the square root of 64?
Yes.
What do I get?
8.
An 8. So the 64 can be removed. Can I take the square root of 2?
No.
No. Could I break it down any further?
No.
Nope, it's prime, so it stays. And we've already kind of answered the question. We couldn't do anything more with x, so it stays as well. So all we can take out this time is an 8, which leaves us with 8 times the square root of 2x.
Okay, so you took from the last problem, that a squared, you technically did like 1 times. So why did that become a?
Why did the square root of a squared become a?
Yeah.
Let me use the 16 to answer your question. Let me answer your question with another question. Good question. So correct me if I'm wrong. Would you agree that the square root of 16 is 4? Okay. Also correct me if I'm wrong. 16 technically could be written as 4 squared. So you're shaking your head yes there as well. What is technically happening is the square root and the perfect square, the exponent of 2, eliminate each other. And what we're left with is the base, which was what was being squared to begin with. So for the same concept, let me bring those back. So square root of 4 squared gives me 4. Therefore, that same pattern, the square root of a squared should give me a. It's really the base that's left over. Same reason back when we were solving equations. If we had something where there was a +3, to make it disappear, we would do a -3. So anytime you see something being squared and you don't want it to be squared anymore, take the square root of it and it gets rid of the squared component. So it's all about undoing what's being done. So good question.
Thank you.
You're welcome. I'm gonna bring up, I think I have 2 more. Yeah, here's the last 2. A little bit more involved. So this next one has something out inside. Now we have 2 variables inside. That's okay. We're still just going to break it down as much as we possibly can. I'm always going to start with the coefficient because that's kind of where we've been practicing. 24, is it a perfect square?
No.
No. Does it have any factors that are perfect squares?
4 and 6.
4 and 6. And there's that infamous 6. We know that 6 can't take us any further. So I'm satisfied with that pair. Then we move on to the variables. X squared. Do I want to break that one down?
No.
Why not?
Because it's already a perfect square.
It's already a perfect squared because it is literally being squared. So x squared is already a perfect square. What about y to the third?
You'll do minus a y.
Well, we don't want to minus a y per se. You want to break a y off. Okay, so that would leave 2 grouped together, but you can't lose the third y because it still needs to be there. We still need to have a total of 3 y's inside before we move on with our next step. So if you think about it, we still have 24 x squared y to the third. All we did was break them down into smaller parts. Now, as I go through and clean this up, can I take the square root of 4?
Yes.
Yep, square root of 4 gives me
2.
2. So the 4 is gone. Can I take the square root of 6?
No.
No. Can I break it down any further?
No.
No. So it'll stay. Can I take the square root of x squared?
Yeah. Well,
You told me it was a perfect
Yeah.
square earlier. So what is the square root of x squared? Just an x, which means it's gone. Can I take the square root of y squared?
yes.
What is it?
Y.
Just a y. So it's gone. Can I take the square root of y?
No.
No. Can I break it down any further?
Yeah.
No, there's only one of them there, so it stays as well. So as I go through and clean this up, I am pulling out a 2, an X, and a Y, and those will also have to multiply with the 8 that was already sitting there. So what's now outside my radical?
16xy.
16xy. And what stayed trapped inside my radical?
4y.
Ooh,
Or 6y.
6y.
Sorry, my 6 looks like 4.
Moving on to the last one. We got a 2 already outside. That's okay. We'll just keep track of it. 45, is it a perfect square?
No,
It is not. Does it have any factors that are perfect squares?
5 and 9.
5 and 9. And I know 5 is prime, so that's kind of a good site. What about m squared? Can I break it down?
It's perfect square.
It's already a perfect square because it is being squared. And what about the n?
No,
No, and it's a singleton, so there's not really anything more I can do with it. Can't break it down any further. You can't add another one in there because there wasn't any more to begin with. So I've broken it down as much as possible. So I go through now. Can I take the square root of 5?
no,
Not nicely. So can I break it down any further?
no,
Nope. So 5 stays stuck inside. Can I take the square root of 9?
3.
Square root of 9 gives me a 3, so it's going to come out as a 3. Square root of m squared is going to give me an m, so it's gone. And can I take the square root of n?
No,
No. So it stays inside. So all that's coming out is a 3 times an m, but it does have a 2 already waiting there for it. So what's going to be outside?
6m,
6m. And what's remaining inside?
5n.
5n. And that, ladies and gentlemen, is simplifying square roots that even have variables inside of them. If I were to boil it down into one simple explanation, if you're trying to take the square root, hope for a perfect square because it'll work nicely. But if it's not a perfect square, check its factors and look for any perfect squares you can break it down into. Because the only thing that we like to see today are perfect squares. So make it work, find them, find the perfect squares.